下部的 program。那我们今天讲者是那个来自于台湾大学的林伟杰教授来跟我们演讲。好，那我帮你查。
谢谢哈维的邀请。So I will speak in English because my Mandarin is not that good, so please bear with me. So today I would like to talk about self-organized criticality. Okay. So what is So today we will talk about self-organized criticality. So before talking about what's meant by self-organized criticality, so let me kind of briefly explain what's meant by criticality. Then this is called a phase transition. And if you fix the pressure and increase or decrease the temperature, then there may be a phase transition depending on the temperature. For instance, if you consider water, then if it reaches 0 degrees Celsius, then it becomes ice. And pressure, and the parameter at which there is a phase transition is called the critical value or critical points. Okay? The critical point is the parameter at which there is a phase transition for some physical model, perhaps.
Okay. Is it possible to translate the gas to solid directly? Is it possible? No.
Of course, in reality, it won't happen. But just imagine that so theoretically, there's a phase transition point, which is in this case, something like 100 degrees Celsius or 0 degrees Celsius. Then 100 and 0 will be the critical points. But of course, in reality, perhaps there's a window instead of just a point. Okay. So usually some interesting behaviors or some structures can be seen around the critical points, and that's why people are interested in this kind of phenomenon. Okay? So let me give you a mathematical model that exhibits phase transition, and this is called Bernoulli point calculation. Okay? So let's consider the integer lattice with nearest neighbor edges, which means if the distance between 2 points is 1, you put an edge there, otherwise you don't put an edge. And then the resulting graph will be something like this. So this is like a portion of the integer lattice with nearest neighbor edges. So if the distance between 2 points is 1, you put an edge, otherwise you don't put an edge, and then you see a grid like this. Okay. And we define each edge to be open with probability p, and define it to be closed with probability 1 minus p. And this open or closed will be independent. Okay. Basically, you can imagine that open edges are the edges that you can go through, and the closed edges are the edges that you cannot go through. So let's see some pictures. Okay. So this is the case when p equals 0.25, which means basically 1/4 of the edges remain in the graph. I mean, you can imagine that the edges remain are open edges, and the edges being removed are the closed edges, and then you get some random graph like this. And from this picture, you will see that there are many tiny components like this, and all the components are quite tiny, as you can see. And when we increase the parameter, say we increase from p equals 0.25 to 0.5, then we see a graph which is more connected. Okay? And it might be difficult to see, but there is a component which is quite large. Okay? Of course, there are some small components, but like this. but most of the components are some of the components are quite large. And when P is getting even larger, then you will see that basically there's only one large quantity components. Okay. And in this case, there is a phase transition because this graph is turning from something very disjoint to some graph which has a large quantity components. So as I said, if you increase P, the resulting graph will become more connected. And when P is small, there are just many tiny disjoint connected components. And when P is large, you can show that with probability 1, there is an infinite cluster, infinite connected components. Okay? And we are interested in when this phase transition will occur. So it will change from many tiny disjoint components to an infinite cluster. So what is the P? So that below that you have disjoint components, and above that there is an infinite cluster. Okay. So it turns out that the critical P is exactly 0.5. Okay. So below 0.5, there are only disjoint connected components, and above 0.5 there is an infinite cluster. You can also consider a model which is very similar to this Bernoulli bond percolation, which is called Bernoulli site percolation. Okay, so the only difference is just this word, sites. Okay. So instead of removing edges, now you remove the vertices. Okay. We say each vertex is open, or sometimes we call it occupied, with probability P and closed with probability 1 minus P. And again, it's independent of all the other vertices. And again, you expect to see some random graphs like this. So when P is say 0.3, then again you see a lot of disjoint components. And when P is getting larger, this becomes more connected, and even more connected when you increase P to 0.8. And for these two models, in order to see the critical behavior, we need to consider a particular P, just like in Bernoulli bond percolation. The critical point is 0.5, so we need to adjust the P in order to see this kind of critical behavior. Okay. But in reality, actually there are lots of models or lots of examples that you can see criticality without fine-tuning this parameter. Okay. So in percolation, we need to change the parameter P to a specific value to see some critical phenomenon. But actually in reality, we don't need to do this. So, basically, roughly speaking, if you see some sort of shape which looks like a fractal, then usually this is what we understood as a critical behavior. And you can see many different fractals in nature without actually fixing a particular parameters. This will appear very naturally. Okay? So this kind of percolation model is perhaps not something that we are hoping for in order to understand what's happening in what happens in reality. So as I kind of explained, basically physical systems will tend to drive themselves towards criticality. They try to kind of converge to the critical points. And this kind of phenomenon is called self-organized criticality. Okay? So in some sense, this kind of systems have the critical points as a fixed point in some sense. So they will try to tend to that particular fixed point. Or perhaps you can view this in another way. This critical point is something like the energy minimizer, and the system will try to minimize this energy, so it will kind of converge to the critical points. Okay. And for this reason, I'm interested in some mathematical models that exhibit this kind of self-organized criticality. So let me first introduce the first model, which is called Abi and Sandpile. So it was introduced by Bach, Kahn, and Wiesenfeld in 1987. Okay. So the model, so they define the model as follows. Okay. So first we consider a box in C2. Okay. And initially each vertex has 0, 1, 2, or 3 grains of sand. Okay. And then you choose a vertex uniformly as random. Okay. The random one doesn't really matter, so just choose a vertex, and then you add a grain of sand to this vertex. Okay. So if the vertex has less than 4 grains of sand, then you go to step 2 and add another grain. But if a vertex has at least 4 grains of sand, then this 4 grains of sand will be sent to its neighbors. And if the vertex is on the boundary, then the grain will just be removed. So let me draw a picture to explain what I mean here. Just an example, so for instance, you consider a box in ZD, and the numbers here are telling you the number of grains of sand on this vertex. Okay? And suppose now you add a grain of sand here, so this becomes 4 now. And now it becomes 4, so it will send the sand to its neighbor, one to each. Okay? So this becomes 0. And then each of its neighbor will increase by 1, so it becomes 2, and then 3, 2, and then 4. And now this becomes 4, it will also send the sand to its neighbor, so this becomes 0, and this becomes 1, 1, 1, and perhaps it sends a sand here, and let's not worry about this. So basically this is dynamic. Just adding sands as random, and if the number of grains of sand is exceeding 4, then it will send to its neighbor. Does mean is that clear?
If the vertex is on the boundary, just remove the
Yeah, just remove the sand. So for instance, if this is a boundary, then you just remove the sand to this vertex. And as you saw, when you send the sands, then perhaps there's another vertex that has at least 4 grains of sand, and then you do the same thing. And after it's stabilized, then you go back to step 2 and add sand. And the reason why it's called abelian, so the model is called abelian sample. So what's meant by abelian is that when we topple the sands, the final configuration will not depend on the order we topple. So perhaps when you send the sands, then there are 2 vertices have 4 grains of sand, and no matter which one you choose to topple first, it won't matter, and the final configuration will be the same. Okay. And this is the reason why it's called abelian. And let's see a picture to see what this kind of sample looks like. So this is the picture. If you have it should be 1 million grains of sand put in the origin, and all the other vertices have no grains, have no sand at all, and then it keeps toppled, and you see some beautiful picture like this. Okay? And different colors just denote different number of grains of sand. And this kind of model, we will kind of refer this to self-organized criticality, because in this model we don't actually have any parameter at all. But the picture we obtain is something, not really a fractal, but some picture that have a rich structure, and we will call this kind of behavior self-organized criticality, because there's no parameter in this model, but yet it kind of exhibits some sort of critical behavior. So in fact, this kind of abelian samples have a lot of rich structure, not just pictorially, but actually algebraically is also something very interesting. So let G be a finite box in Z2, okay, just a finite graph. And then we choose a particular vertex of G and call it sink. And all the grains that fall into the sink will be removed. And so we ignore all the grains that fall in the sink. Okay? So we choose a particular vertex, and if a grains of sand is sent to this vertex, then it will be removed. Okay? And then you consider M to be the set of the stable stem powers of G. So as I said, so after you add a grain of sand, then it will send to its perhaps the grains will be sent to its neighbors. And after several steps, then all the vertices have grains of sand no larger than 4, no larger than 3. Then this is called stabilized. And we let M to be a set of all stable sand powers. And if you add two stable sand powers together, and then after that you just stabilize the sand power, and this gives you a algebraic structure. And in fact, this is a commutative monoid, and monoid is just basically a group without inverse. Okay? So basically, you add two sand powers together, then perhaps some vertices have number of grains of sand more than 4. Then you need to stabilize the sand power. But after stabilization, it becomes of course, a stable sand power, and this gives you a algebraic structure. And in this monoid, we can define ideal just as in grain. We define ideal to be a subset of J, just as sigma times J is a subset of J for all sigma in M. And we can define the sand power group to be the minimal ideal of M. Okay? We can show that because M is just a finite set, this minimal ideal is indeed a group. Okay? This is something that you can show. And although in the beginning I said that G is a finite force of Z2 in Z2, but you don't actually need this particular graph. You can also actually define this sand power group Kg on any finite quadratic graph. And this and it turns out that the resulting group does not depend on the choice of the sink. And I mean the resulting group will be isomorphic to K of G, no matter which sink you are picking. Okay. So we would like to understand this group K of G. So one particular question that you can ask is, what is the identity element in this K of G?
So even though M is not a group, we end up with a group K of G.
Yes, M might not be a group, but the minimal ideal must be a group. Okay? This is something that you can show. If you have a monoid which is finite, then the minimal ideal must be a group. Actually, I don't know how to show this, but I just figured this. Yeah, so basically, you can try to understand what this K of G is. And one particular question that you can ask is, what is the identity elements of this K of G? Yeah.
Why do you need a sink here? If you don't have a sink, can you still define?
Let me see. If you don't have sand, then the sand power might not be able to stabilize. Because perhaps some vertex will have too many number of grains of sand, and it will perhaps go around the graph, and then they will not stabilize. So you need you need to remove some sand in order to talk about stabilization.
边界点算是 sink 吗？边界点算是 sink 吗？
什么算是
The points on a
boundary
boundary.
point is count as a sink.
Yeah, you can think in this way. Yeah. I mean, you can kind of identify what the boundary points at a particular vertex and consider that as a sink. This is one standard way to define a sink, but it's not necessary.
Would you remind me again what the minimal ideal is?
Minimal ideal, just any ideal. Let me see. Minimal ideal means if you have an ideal which is smaller than the minimal ideal, then it will be that ideal itself.
Maybe I should change it. In this example, what does it mean to be an ideal?
Ideal is just, let me satisfy this property. If it's a subset, that sigma times J is a subset of J, or sigma in M. And you consider the minimal one which satisfies this property.
Can you use the graph to show us an example of linear ideal?
It would be.
It will be difficult.
Yeah, but I will show you next slide what does the identity look like.
But if you apply sigma to J, in general, the number of grains will increase. Unless it's sync elsewhere.
But you consider the configuration so that the sample is stabilized. So,
but if you add something to a stabilized computer,
yeah, you need to do some. Yeah.
Increase the number of grains.
Yes. Yeah. But perhaps some of them will be sent to the sink, so it might be fine. There's a sink that allow you to remove the sands. Does that make sense? So any other questions?
Can you explain again about the operation in the addition?
Yeah, so you have two samples, then you can just add two samples together because they're just numbers on the vertices, so you just add the numbers. And perhaps some of the numbers will exceed 4 in this case, then you need to stabilize it, send the sense to these neighbors and so on. And after a finite number of operations, it will be stabilized. So we're interested in this group K of G. And now if you consider a box, which is 523 times 523, and you identify all the boundary vertices as a sink, then the identity will look like this, okay? Which is very beautiful. And you can see that this sample group is something very complicated because the identity itself is already very complicated. And again, different colors mean different number of grains of sand. Okay. So basically, you can view this samples as some elements of, you can view this as a vector, okay, C to the V, where V is the set of the vertices which are not sync. Okay. And then you can do addition as above. Okay. And basically, when you topple a vertex, which means you send the sense to its neighbors, basically it corresponds to adding a vector to this configuration, okay, where you remove the remove the sense. It's like a toppling because if you have DV many neighbors, then you just send one grain of sand to each neighbor. So you need to subtract this number in order to topple the sense. Okay? And if V is a neighbor of W, you just send a grain of sand to that vertex and 0 otherwise. Okay? So this corresponds to basically sending 4, rating 4 as 0 and then add 1 to its neighbors. Yeah.
Maybe I understood something. Is the identity of this group not 0? I mean 0.
Yeah, the identity is not 0.
Why not?
Because the sample group is the minimal ideal, and if the minimal ideal contains the identity, then you will be the whole monoid, and you shouldn't be the minimal.
So 0 is the identity of monoid.
Right.
But it's not identity of this group.
Right.
Okay, thank you.
So it's kind of interesting. Yeah. So we can define a equivalence relation. So we say that two configurations are related if it is a linear span of this kind of vectors. Okay. And then you can show that actually each equivalence class has exactly one element in K of G, and because of this K of G is actually isomorphic to Z to the V mod delta times Z to the V. Okay. And this matrix delta is also called the reduced Laplacian. The reason why it's called reduced because we just consider all the vertices which are not sync. Okay. So one of the vertices is removed, so that's why it's called reduced Laplacian. But basically it's just the same as a graph Laplacian. And this matrix delta has some nice combinatorial object associated with it. Okay. So if you compute the determinants of this matrix delta by the matrix tree theorem, this is accessing the number of spanning trees in the graph G. Okay, so there's some graph theory things that perhaps you might not have heard of, but this is something true. Okay. And on the other hand, the determinant is also the index of the subgroup delta Z to the V in Z to the V. Okay. So in particular, the number of elements in this K of G is excessive to the number of spanning trees in G. Because the index is just delta of determinant of delta, so that's why this is the same as the number of spanning trees in G. Yeah.
The graphical function has a constant kernel, right?
Sorry?
The graphical function has a kernel, the constant.
Constant.
1 everywhere.
Yes.
So why is the determinant not 0?
But you remove the sink, so you remove a particular column and a row. Yeah. So this is the reason why this delta every determinant is not 0. Okay. And I just want to mention a few words that this has some rich structures and closely related to algebraic connectorics, which I don't actually know too much about it. But I can only say that one of the person who received field medal recently, I don't know how to pronounce his name, Jun He. Okay. He works in algebraic combinatorics, and some of his work is actually related to this abelian sample in some way. I'm not sure how it's related, but I was told that they're related. Yeah. So this abelian sample is something very interesting, okay, and have a lot of combinatorial structure behind. Okay. So this is what I want to say about the abelian sample. And next we will move on to another model that exhibits sample mass criticality. Yeah.
What's the spanning tree? The spanning tree. What is it? What is a spanning tree?
So if you have a graph, a spanning tree is a subgraph, which is a tree, and it takes all the vertices in the graph. So for instance, in this graph, then this is a spanning tree. It spans all the vertices. It has all the vertices and at the same time it is a tree. So there's no cycle, and it uses all the vertices in the original graph.
What do you mean there's no cycle?
No cycle means that there's no loop like this.
What is a loop?
Just a circuit. You can go from point to itself by there exists a hash self-aware walk from this point to itself.
But that's a loop, right?
Yeah, that's a loop. But a tree is a graph which has no loop.
I'm sorry?
A tree is a graph which has no loop.
So here there's no tree.
If you consider the yellow part, there's no loop, and so this is a tree. Does that make sense?
I cannot distinguish point from here.
So if you remove these edges, then now this subgraph is a tree. So this is a particular example of spanning tree of this graph with 9 vertices. So a tree is just a subgraph, so that the vertex set is the same as the original graph, and at the same time it is a tree. Does that make sense? Any other questions?
So we saw some pictures about the stabilized stabilized samples, and then how would one show, or is it possible to show this is actually something that is in this critical point or parameter?
Yeah, this is a good question. Actually, we don't really know whether it is a critical point of some particular system, but this is like a simplified model. Just like you imagine that you add some sand on the table, you keep adding sand at a particular point, and the sand then is spread over the table. And basically this model, this sample model is kind of model this kind of phenomenon. Perhaps when there are too many sands in a particular points, then you will topple. Okay? And this kind of model, this model is just a simplified version of this kind of phenomenon. And basically we are looking at the configuration where the energy kind of is minimized. So in this sense, because it's kind of minimizing the potential energy of this kind of sample. But you don't need to adjust any parameter in order to see this kind of picture. So that's the point. So any other questions? If no, then we move to another thing called the forest fire model. And it was introduced by Drossel and Schwab in 1992. Okay. And this model is perhaps slightly more complicated. Again, you consider integer lattice, and initially all the sites are vacant. So sites means vertices. So all the vertices are vacant. And then trees will grow. So each site will be occupied by a tree at raised one, independent of all the sites. And then at each tree, there will be some ignition occurs at raised theta. You may imagine that there's some light length that will kind of burn the tree. And this light length process is independent of the growth process. And then when there's an ignition, then the tree is set on fire and it will burn for a random time, which mean delta. And when it's being burnt, the fire may be spread to the adjacent trees with raised lambda. Okay. And then when a tree is burnt, then the site will become vacant again, then it can be occupied by a tree later, and so on. Okay. And this is a very simplified model for forest fire. But as you can see, there are already many parameters like theta, delta, and lambda, and it is complicated. So let's try to understand a simplified model. Okay. So let's consider the model with theta and delta going to 0 and lambda going to infinity. Okay. So basically, the ignition will occur at a slow rate, theta, very close to 0. And the delta is the time you burn a tree, and when delta is tending to 0, it means that the time you burn a tree is 0. Okay, because tree will be burned instantaneously. And when lambda goes to infinity, it means that the rate at which the fire is spread is infinite, which means the fire will be spread to its neighbor again instantaneously. Okay. So you can understand this as follows. Basically, whenever there is an infinite cluster, when you burn it, then the whole cluster will be burned. Because because when theta is set, if you set theta to 0, if you have a finite number of vertices, then it will not be burnt. But when you have an infinite number of vertices, then perhaps it might be burnt. So basically, this can be interpreted as whenever there is an infinite coordinate components of trees, then the whole forest will be burnt. Okay. So let's try to consider this model. Just reworded what I said. Okay. So initially all the sites are vacant, and then the sites will become occupied with raised 1. And when there is an infinite cluster of trees, then you will burn the whole cluster. And when after the tree is burned down, the site is vacant again, and then you will just, and it may be occupied again and again. Okay. So let's consider this model. So this is a good candidate for self-organized criticality, because basically, if you ignore this burning, if you just allow tree to grow, then basically this is the same as Bernoulli site percolation we defined in the beginning, in some sense. Because tree grows randomly, and it corresponds to the sites become open randomly in some sense. So this model without burning is basically just Bernoulli site percolation. And whenever there's an infinite cluster, then the cluster will burst. And let's recall, we see an infinite cluster when the parameter is above the critical points. So basically, what you are burning is something kind of exhibits the behavior that is close to the critical points. So that's why this is a good candidate for self-organized criticality, because this model is not parameter at all. And then you can see some critical behavior. I mean, you expect to see some critical behavior. Okay. But unfortunately, you can show that actually this model cannot be defined mathematically. So basically, you can show that this stochastic process does not exist. Okay. It cannot be defined as a stochastic process, although it seems that intuitively it is something that you can define. So as I said, if you forget about the emissions, then basically this is the same as Bernoulli size population, and with some parameter, and the critical time will occur at, let's say, this point minus log of 1 minus PC. So you don't need to understand how this comes from. Just basically, if you translate all the things in terms of time, then it should be given by this value. Okay? And this PC is the critical points for Bernoulli size population. Okay? But in any case, basically, I mean, the interesting phenomenon we have in our TC, and basically, I mean, what I'm going to kind of convince you is that this model does not exist. Okay. So, from some theory in population, we know that at the time TC, there is no infinite cluster, but when T exists TC, then there is one infinite cluster almost surely. Okay. And you can also show that in some sense, if T is greater than Tc, and if you burn the infinite cluster, because we know that there is one, and if you burn this, then because this infinite cluster has a positive density in some sense, so if you burn it, then you need a fixed amount of time epsilon to create another infinite cluster. Okay. So if you burn a cluster, then you burn too much, and you need to waste a certain amount of time to see another infinite cluster. Okay. But well, we know that if a cluster is burned at some time, it must be greater than Tc, because we know that at Tc, there is no infinite cluster. So a cluster must be burned after some time T1. Okay. But you know that because T1 is greater than Tc, you can find another time T2 such that it is greater than Tc, but less than T1. But we know that at T2, an infinite cluster has already, exists. Because whenever T is greater than Tc, you see an infinite cluster. So if T2 is greater than Tc, then you will see a cluster already at time T2. And similarly, there is another time which is between Tc and T2 such that there is already an infinite cluster. So basically, this kind of addition times will have an accumulation point. But this will be like a contradiction because, as I said, if you burn an infinite cluster, then you can wait a certain amount of time to build another infinite cluster. So this is impossible. You cannot define this model, basically. So it's shown by Vandenberg and Brouwer that this model does not exist under some unproven assumption. And the complete proof was by Kiss, Manolescu, and Sidorofecius in 2015. So it took like 10 years in order to show that this model really does not exist. And something interesting to notice is that we can actually define this model on tree. If you consider infinite spiral tree, then you can actually define this for a spiral model. But on Z2, you cannot define this model. It's kind of interesting. Basically, because the main reason is that for Z2, the infinite cluster has a positive density, but for the one in tree, the density is like 0. So basically, even if you remove an infinite cluster, it doesn't matter. Okay. So because this model does not exist, so let's again try to simplify. Study a model which can be defined mathematically, and at the same time we can analyze. So let's fix a large integer n. Okay, now we are not burning an infinite cluster, but we burn a cluster of size which is at least n. Okay, so again, initially all the sites are vacant, and then it becomes occupied by tree as raised 1 independency. And then whenever there is a cluster of trees of size at least n, then you just burn the whole cluster. Okay, so you are not burning an infinite cluster, but burn a large cluster. And to simplify the model, let's assume that when trace burns, then the sites cannot be occupied again, so it will stay burned forever. Okay. And now this model can be defined because it just involves some finite range. This is a finite range process, so this can be defined. Okay. And this model is also called frozen percolation, and we interpret that the clusters is frozen when it gets large. Okay. But for us, let's just stick with the word forest fire and understand this in terms of forest fire. Okay. So let's see some summations. Okay. So here, this is the forest fire model with difference n. This is when n equals 10, this is when n equals 100, and this n equals 1000. Okay. And each colored cluster is a burned cluster. The white one will be the one occupied but it is not burned, and the black one will be the vacant sites. Yeah. So basically, you see that when n is 10, of course, there are lots of small clusters. But when n is getting larger, you see some kind of fractal behavior. Okay. And the burned cluster is basically it looks like this. Okay. So we want to try to understand the geometry of this kind of burned clusters. Okay. So this is our goal. And this question is of course quite difficult, so let's try to ask a simpler question. So what is the probability that the origin is burned in the final configuration when n is getting large? So what would you guess? What are they going to guess? So let me tell you the answer. It's actually a problem. So we don't have, this is one is no. And the condition is that it should go to 0 at n goes to infinity. So because when you consider this forest fire, because you need to look at the whole integer lattice, and because it's an infinite graph, and it is, to study this kind of problem, it will be difficult. So one possibility is to try to restrict the process in the finite box and try to study the process in this box. And perhaps let's the size of the box tends to infinity, then perhaps you can say something on this probability. So this is one way that you can try to restrict the process in the finite box and try to study this process. Okay. But it turns out that even if you try to restrict the process in the finite box, there is some strange behavior because this process is very sensitive to the size of the box. Okay. So it was shown by Vandenberg and Nolan that there is a sequence of scales which are called exceptional scales. Basically, it tells us that if you consider the forest fire model near this exceptional scales, then the behavior is different from the other scales. Okay. So basically, if you consider a box of side length which is close to mk and study for the progression in this box, then you can show that this probability 0 is burned is 1 away from 0. But if you consider for the progression in a box which is far from these exceptional scales, then this limit, the probability that 0 is burned is actually tending to 0. Okay. So in other words, even if you restrict the process in a box, the behavior is very sensitive to the size of the box. If it is close to mk, then this probability is 1 away from 0. And when this box, the scale is far from this mk, then you guess, this probability will go to 0. So if you want to use what happens in finite box to compute what happens in the plane, it will be very difficult. Actually, it's impossible. So let me use some time. Let me try to let me skip this one. This is going to skip this. Yeah. So as I said, you cannot conclude anything from the finite case because you have two kind of different behaviors. So you cannot say what happens if you consider the model on the whole integer letters. But if you change the letters to the triangular letters t, then you can say something more. Okay? You can actually show that this limit indeed goes to 0. Basically, it is it follows from the fact that if you consider Bernoulli size progression on the triangular lattice, then in some sense there is a scale limit which is related to the so-called Schrödinger evolution. Perhaps some of you were in the colloquium of Izuman last week, and he probably talked about this. Basically, if you consider size progression on the triangular lattice, then basically, at the critical point, it converges in some sense to S76. Then you can use some tools in stochastic calculus to help us to describe what happens for critical size progression on the triangular lattice more precisely. And this can be used to study the force-field model on the triangular lattice. And you can initiate that this mk is of order n to delta k, where delta k is this number. And you can also show that this limit indeed is 0. So this is the reason why we conjecture that the limit on Z2 is also 0. So how we wait again? Is 450 or 5?
55, I think.
55.
Because we started it.
Yeah, we started. Thanks. Yeah. So yeah. So let me talk about another forest-field model. So just now we consider a model where you burn a cluster when the size of cluster is large. Okay. Now instead of burning large cluster, okay. So again, initially all the sites are vacant. And now let me emphasize, we now consider the triangular lattice, okay, because of the reason I talked about just now, because there's some better description for progression on the triangular lattice. And again, the sites become occupied at raise 1. And now we have emissions, which occurs as raise zeta, so it's such a lightning, which burn the clusters. Okay. And when a tree is burned, then the whole cluster will be burnt. And again, the sites cannot be occupied again if it's burned, just for simplicity. Okay. And you can show that this model can be defined. And basically, this is very similar to the previous model with n equals zeta minus 1. Because if you have a cluster which is of size zeta minus 1, because emission occurs at rate zeta, then with positive probability, this cluster will be burnt. So basically, it's like when it gets large enough, then it will be burnt. And the parameter is basically like zeta minus 1. But this model is more complicated because the emission can happen very early, and this will change the environment a lot. But you can also show that there exists, again, a sequence of accessible scales. Basically, if you are close to the scales, then this probability that series burns is found away from 0. And if you consider a scale which is far from this accessible scales, then the probability will go to 0. But these two accessible scales are slightly different. When you consider the zeta model, which means the model with emissions, then delta k prime is given by this number. Don't ask me how this number comes from, but just these numbers. But if you consider the model which burns a large cluster, then the delta k is slightly different. And for these two kind of models, you can ask the following, because you can informally just take k tend to infinity, then this becomes 48 over 55. And this when you take k to infinity, this becomes 48 over 91. So you might ask the question, what happens when you consider the model at the scale n to the power delta infinity or zeta to the minus delta prime infinity? So it turns out that if you consider the model in which you burn large cluster, then if you consider the number of burned clusters around the origin, then if you divide this by log of n, this in some sense converges to a number which is given by log of 96 over 5 inverse. So basically it says that if you consider the number of burned cluster that surrounds the origin, if you consider the model in this box of size m infinity, then this divided by log n will converge to this number n. And if you consider the model with light length, the zeta model, then you have a similar phenomenon. If you consider the number of Bernoulli clusters that surrounds the origin, if you divide by log 1 over zeta, this will converge to some number, 96 over 41. So basically, if you study the models in this m infinity scales, this is how to say, quite complicated, and this kind of phenomenon is quite surprising because not only you can show that the order is log of n, but in some sense there is a law of large numbers for this kind of number of Bernoulli clusters. So of course, one thing that you can ask is what happens if you consider a scale which is much larger than m infinity? So actually, I think not much is known, but we expect that basically if you consider the model in a box of size which is much larger than m infinity, then there won't be too many clusters that surround the origin. All the clusters that surround the origin should be close to the box, should be in a box of size m infinity. Okay. And just one remark is that basically you get the same conclusion if you consider the forest fire on the whole plane and you consider the number of Bernoulli clusters in a box of size m infinity. Okay. And I think because of time, let me skip the proof and let me end here. Thank you.
So, question or comment for our speaker?
Okay, if not, let's send our speaker again.